Ladies and gentlemen, thank you for coming, for taking time of your busy day. I would like to thank UT Science Forum for inviting me, and Mark for all the help with working out the details and for the very nice and kind introduction. So I will be talking to you about molten salt reactors. First, I would like to recognize Kirk Sorenson, who sort of did a lot of work bringing this technology into public, and especially mine eyes back more than a decade ago. He is a founder of Live Energy, and he also was my first graduate student. If you want to know a lot about the history, I would recommend his thesis, The History of Thorium Research in Manhattan Project Era, which can be found on UT website. And I also stole a lot of his slides. Now, before we do that, I would like to introduce the current situation as far as energy is concerned in global context. I think there's a lot of happy talk about that area currently. So I would like to sort of present the situation as I see it. So if you look on the global scale, both per capita and in terms of our past ancestry, we have increased our per capita energy extraction dramatically. And the reason is that as we are progressing with our technological capabilities, what technology does in broad terms, it allows us to extract economic utility out of primary resources. And the better the technology we have, the more economic utility we can extract out of these resources. So this is reflected to its relation to GDP, and you can sort of see the orders of magnitude rise as we go from primitive societies through agriculture, early industrial, to where we are now. You can also plot this table in terms of its components, and then in total megacalories per day per person. Now, the units I like are watts, like average watt per person. Everybody can imagine how a 100-watt bulb looks like. Right, so if you think that the 10 100 watts bulbs are online 24/7, that's a kilowatt of average energy consumption. And so in the United States, we are roughly at 11 kilowatts per person. And how much is that? So we can come up with a non-SI unit of energy slave. So if you have a slave working for you 8-hour days, they can make about 60 watts of labor. So that's that unit. So you can calculate easily that our living standards are about 550 slaves per person as far as the energy is concerned. Now, of course, this machine takes about 60 watts. It can run 24 hours, and it can deliver messages at the speed of light around the globe, which no slave can do. So if you think about it, the point is we are living in the golden era, which nobody has ever seen before. And the level of luxury which we are enjoying now is absolutely unprecedented to the point that we fail to realize. So that's the first point I would like to make. Second point is that if you look at the quality of life indicators, they can be infant mortality, HDI, life expectancy, political freedom index. It doesn't really matter what you take. They correlate with energy consumption per capita. Now, in these plots, the United States is in the far right, but there are, of course, countries which have higher energy consumption than United States, Canada, the Gulf countries, and so on. But that's not the point. The point is that if, according to all these plots, if the energy consumption drops, goes down, the life quality worsens. And you can kind of see that if you are at 1/2 of US current economic consumption, energy consumption, the life is still reasonable, right? If you drop much below that, it gets bad very quickly. So we can recognize that this amount of energy consumption appears to be required for decent living standards, no matter where you are. Now, you may have seen this plot that as far as fossil fuels, we are here and we will run out of fossil fuels. Now, I hope to offer some more hopeful message at the end. This is where our energy currently comes from. So our coal, oil, and gas is coming from, is covering about 85, 86% of energy needs. Then we have nuclear, then we have hydro, then we have combustion of waste and biomass. And the orange sliver on top of it is wind, solar, geothermal, tidal, and everything else. So now notice that often these two categories are grouped together, but most of the wastes which we are combusting are fossil fuel derived, like all the plastics are fossil fuel products. So they are as renewable as the primary resources, meaning the oil and gas. And things like trees, whale oil, and other natural fuels, I don't think are very renewable at the scale we are talking about, especially if you consider the amount of energy which we will need going forward. Now, we can partition this into a developed world, OECD countries, and you can see that we have peaked somewhere in early 90s at about 5 billion tons of oil equivalent energy consumption, plus minus 10%, and this consumption is kind of steady. And this corresponds to the developed countries reaching the advanced industrial age. And so what can we do in the developed countries? Now you can see what Germany has done. This is their, depending how you count, maybe $1 trillion on infrastructure, in the spending on wind and solar. And compare it to, say, France, which in 1970s decided to decarbonize via nuclear power with orders of magnitude less expenses, and you see where they are. Now, they still drive cars, so electric cars. They still have a chemical industry, but that's hopefully might be tackled by technologies I will talk about. If you compare it to the developing world, this is the same 5 billion of tons of oil equivalent when the developed world has kind of stabilized, right? And energy consumption is growing dramatically. Now, why is that? And the reason is that they want to have the same living standards as we are. So can we understand where are we going? So I mentioned earlier that it appears that half of US energy consumption is required for decent living standards. So let's come up with this utopian, idealistic world where everybody, including the United States, either lowers their energy consumption, in the United States case by half to 5.5 kilowatt, and everybody else either grows or reduces their energy consumption for this 5.5 kilowatt. And then we realize that we need 3 times more energy. Now, of course, we have 7 billion people now. They're going to reach 9 billion, so that's times 4. And as you know, utopia is not one place. Utopia means no place. So we are not going to reduce our energy consumption. So realistic estimate might be times 5. So, and you might wonder yourself, well, what about nickel, iron, copper, lithium, other sources? If you read this paper by Weinberg and Geller from the year I was born, energy is the ultimate raw material. If you have that, you can substitute one thing for another. So I think it really boils down to energy. Now, at the same time, we know that we need to reduce our greenhouse gas consumption by 80% or more, while we need to grow energy production by a factor, let's say, 3 to 5 to make life on Earth bearable and stabilize population, because population stabilizes when people are wealthy. So we need to come up with clean energy source that is cheaper than fossil fuels fundamentally, because the developed world cannot afford to overpay for their fundamental energy. And if you believe the climate models, we have about 30 years to do it. To basically reduce the energy consumption of fossil fuels by 80% while increasing the total energy consumption. So that seems to be quite a challenge. So sometimes some point about the anthropogenic global warming, it's not that the CO2 would warm up the planet, it's that the CO2 adds a blanket over the planet, and then as much as if you add a blanket over yourself in the night. It's not the goose who's warming you up. When if you have goose feathers in the blanket, right? It's the insulation capability of the blanket to trap the heat, and then your heat will warm you up. So that the same thing is basically happening. So it's not like that we have reached where we're going. We have created this inequilibrium where the heat is rising up, and the imbalance is about 0.6 watts per square meter by best estimates with large error bar. That's barely a candle per meter square, but there's a lot of meters square. So if you multiply it, you get 310 terawatts. What is that? And that's about 130 times our average global power consumption, or 4 Hiroshima-type nuclear explosions every second. So that's a lot of heat which is being added into the planet, and we are just beginning to notice the changes if the predictions are correct, which they seem to be. So what can we do? Now, so far we have been focused on lowering fossil fuel consumptions in the developed world. And I posit that this is futile, because the way we do it is that we are replacing fossil fuel by expensive schemes which the developed world cannot afford. So if we lower fossil fuel consumptions in the developed world, the only thing which will happen is that the fossil fuels would get cheaper on global markets, and they just get burned faster or at the same speed. So because developing countries cannot afford to overpay for energy and will buy whichever one is cheapest. So it's not just futile, but I think it's a waste of effort, it's waste of money, it's waste of people's time to invest in expensive energy production schemes. Our only chance is to develop energy production which is fundamentally cheaper than fossil fuels, so people who cannot afford to overpay it will buy it because they are economically incentivized to do so. And if we don't reach it, then it really doesn't matter what we do here. Now, of course, I usually talk to students. I would tell them that they should count their blessings instead of tilling the soil in some sort of a subsistence agriculture situation. They can study and become an engineer, scientist, or entrepreneur, which is wonderful. So I think this is the charge of the developed countries to came up with clean energy which is fundamentally cheaper than fossil fuels. And this was recognized early on. So people often show this part, but they never show this part. It's from King Hubbard paper from 1956. This is the famous peak oil paper. And there was another curve. It was a curve with nuclear power. And why are we ramping up on nuclear power production? There are some reasons. There are some reasons which keep the current nuclear power back. And they can be put into several categories. So current nuclear power produces what's called a spent nuclear fuel or nuclear waste. And we have been trying as a scientist to persuade the public that, okay, this is just a solid stuff which sits somewhere, doesn't harm anybody. But I think we have failed to persuade the public to make this case. So we need to get rid of it, at least in democratic societies, to be able to expand nuclear power by a factor of 60, which is kind of what we are talking about from the beginning. How can we improve safety? Instead of engineered safety in the nuclear reactors, can we design reactors which are inherently safe so that they do not rely on some engineered systems to provide safety action? Can we address proliferation? Can we come up with the fuels which are much more difficult to weaponize and basically eliminate enrichment from the supply chain? Can we reduce water cooling requirements? So the current large reactors, because of the heat engine type they use, the Rankine cycle, they virtually necessitates use of water cooling for the condensers. This limits siting. Can we build reactors cheaper? So if we have reactors which run at ambient pressures instead of at high pressures, we can make the primary system thin-walled because it doesn't have to contain the pressure. We can make a closer fitting containments if there is no phase change, which would increase in volume. And perhaps we can use compact gas turbines instead of these steam turbines. The gas turbines are much smaller in size, so much cheaper to manufacture for the same power production. But they require high temperature reactors. So that's sort of very much oversimplifying where we are. So what coolant choices do we have for a nuclear reactor? If you think about it, we can have coolants which operate at different temperatures, low to moderate temperature and high temperature, and different pressures. So currently, we are using light water reactors, which can only operate at moderate temperatures and require high pressure. That's the opposite of what we want. We want low pressure, high temperature systems. An alternative here would be liquid salts. And so I don't want to talk much about how did we get here, because that would be a talk on its own. But let's just recognize that we are not really using the optimal coolant for our reactors. Another attribute to be considered in reactor design is what is the heat capacity of your coolant. So if you look at water, it has very good volumetric heat capacity. And that's the reason why it's often used in power engineering. And but if you look at the liquid salt, in this case it's a salt called FLiBe, lithium fluoride and barium difluoride eutectic, it has even higher volumetric heat capacity. Not by much, but that seems to be a slight improvement. Why go to high temperatures? Obviously, the higher temperature, the more efficient heat engine you can connect to your machine. It's just the Carnot cycle consequence. However, if you have high enough temperature at the outlet of your system, you can drive many of industrial applications directly without having to go through the heat engine in the first place. So here are some temperature ranges for a bunch of salts, and here are temperature ranges for industrial processes like petrol refining, oil shale, sand processing, cogeneration of electricity and steam, steam reforming of natural gas, and biomass gasification, electrolysis, hydrogen production, coal gasification. You could add various melting temperatures of metals and glasses. Basically, once you are at these high temperatures at roughly above 600 C, there is a lot of industrial applications where you can use the heat directly in the industrial processes, therefore much efficiently. We talked about the spent nuclear fuel and why it's a problem. So let's look at the composition of a regular spent nuclear fuel. This is a standard Westinghouse fuel after 3 cycles of irradiation. And you start with the fresh fuel, which in this case is 3% uranium-235, and the rest, the 97% going down to the foundation base rock, is uranium-238. Now, after the 3 years of irradiation, you still have about 1% of uranium-235 and 236, and another 6% or so of uranium-238. So in total, about 96%, 95% of the uranium, of the material you have is still uranium, which if you could separate it, you could just dump back in the hole where it came from, or re-enrich it and reuse it. Then we have 3% of fission products. The largest one is xenon, and they are highly radioactive, which means they are decaying very, very quickly to stability. And almost all of them has a variety of potential applications. So xenon, for instance, is wonderful for ion engines, and NASA would really like some xenon. Now here's the problematic part. This is a plutonium, and you see most of it are isotopes of plutonium plus tiny sliver of minor actinides, the transplutonium elements, which have long lifetime. They're fairly radioactive, so plutonium-235 half-life is about 24,000 years. multiply it by 10, in 10 half-lives you get rid of it, and that's your 250,000 year, that's your time for geological repository. So this is the problematic part. However, they are useful fuels. We can use them as a fuel. Now I have a 4-year-old, and what sometimes happens is that my 4-year-old comes to the kitchen, and from the configuration when we have a milk, ketchup, sugar, salt, becomes a big waste pile, right? And that's where we are, right? If we were able to partition all of these, then they are very, very valuable. But they are locked in the spent fuel rods, and they are hard to get to. So that's the technology to partition them and separate them back into their separate containers. Currently is very expensive. Now, if we could do it, and here's a DOE slide, relative toxicity of spent fuel, if we do nothing, that's the red line, right? So we get to radiotoxicity of uranium ore in about 250,000 years. Now, if we remove plutonium, uranium, and minor actinides, so the transplutonium element out, we end up with something that needs to be shielded from environment for 300 years. I think everybody would believe us that we can engineer a barrier that will last 300 years. When you're trying to persuade the public that you can engineer a barrier which will last 300,000 years, it gets a little more problematic. So, of course, if you burn all the fuels, or the possible fuels, then you increase your fuel efficiency. So here's a comparison of our current nuclear fuel cycle with sort of idealistic, fully closed nuclear fuel cycle, where we are trying to make a gigawatt of electricity for 1 year. In our current fuel cycle, we start with 250 tons of natural uranium. We enrich it. We end up with depleted uranium and enriched uranium. 35 tons of the enriched uranium is sent to a regular reactor where we burn it. We end up with 35 tons of spent fuel that needs to be handled. And out of that 35 tons, we have 1 ton of fission products, 34 almost tons of uranium, and about 300 kilograms of plutonium and higher actinides. So these are the useful fuels. Depleted uranium is also a useful fuel. So in our hypothetical closed fuel cycle, we will take actinide fuel, burn it, come up with 1 ton of fission products. Within 10 years, 83% is stable and can be partitioned and sold, and the rest we need to isolate roughly 300 years. However, if you think about it, many of these radioactive, longer-term radioactive elements have applications because of their radioactivity in industry, medicine, sanitation, things like cesium sources and so on. So there are potential applications. So why don't we do that? And one of the reasons why don't we do that is that it's very hard to burn this solid fuel which we are using currently completely. The reason is that the ceramic matrix which forms the solid fuel gets damaged by fission products. So the uranium atom, when it gets hit by neutron fissions, basically explodes. The 2 fission fragments depart by a fraction of the speed of light, leaving the electron cloud hanging and kind of looking what just happened. And then they decelerate by ionization losses in that matrix. And that deceleration damages the chemical bond structures of the fuel. The same can be said about the gamma rays. So the sort of gamma rays in the nuclear reactors, when they interact with the nuclei, they would rip the chemical bonds apart. Neutrons, even if they don't cause fission, they transfer enough energy to rip the bonds apart. So that's one factor. Basically, the mechanical stability of the fuel limits its lifetime. You can see that the fuel is not very good conductor. The ceramics is not very good heat conductor. So there is a tremendous temperature profile over the fuel pellet size. So all these factors contribute to mechanical degradation of the fuel form. Additionally, in particular in our current thermal reactors, many of the fission products are poisons. Well, poisons meaning they eat neutrons, so they poison the chain reaction. And at some point, the fuel contains such a high amount of poisons, a low amount of fissile elements that you have to take it out. So can we find a solution? Solution, which I propose, or which was proposed many years ago, is use liquid fuel. And specifically, liquid fuel in the form of ionically bonded alkali halide, in this case alkali fluoride salts. So instead of the covalent chemical bond, we have an ionic bond of a liquid. So if there is a radiation damage, the ions just reorganize themselves. Right? There is no sort of a permanent damage of the ionically bonded liquid by radiation. Additionally, these alkali fluoride salts you take the most electronegative element, fluorine, you chemically bind it with the with the least electronegative part, like alkali metals, and then you create the most stable chemical bond you can create. So it doesn't try to react chemically with anything, unlike, say, sodium coolants. And also, this chemical stability leads to very wide liquid window, which is liquid under atmospheric pressure. So you have something which is chemically stable, doesn't need any pressurization, and has a liquid window of 1,000 degrees, dissolves uranium and other actinides, and also binds some of the very problematic fission products like cesium and strontium. They create stable fluorides, which are dissolved in the melt. So you might ask yourself, well, that sounds great. Why did anybody think about it before? And the truth is they did. So this concept was invented in early 1950s by R.C. Bryant at Oak Ridge in the effort to build a nuclear-powered airplane. So when you have we all know about nuclear-powered submarines, also reactor invented at Oak Ridge. But Air Force wanted to have their own nuclear-powered aircraft. So they tried to figure out what could power jet engines. The idea was, can we provide the heat externally to the jet engine? Instead of the combustion chambers, we would just have a heat exchangers. And they came up with this fluoride salt fuel form. They actually ran in 1954 for 2 weeks. They ran aircraft reactor experiment, which ran it for about 2 weeks. Then they designed a fireball reactor, which was aircraft reactor test, sort of a prototype for an engine that could drive an airplane. But in the 1960s, we figured out intercontinental ballistic missiles, which were much better alternatives, so the whole program was scrapped. I could talk about the aircraft reactor experiment, but maybe it's too technical. Alvin Weinberg then said that it wasn't that I suddenly became converted to a belief in nuclear airplanes. It was rather that this was the only avenue open to Oak Ridge for continuing in reactor development. That the purpose was unattainable, if not foolish, was not important. A high-temperature reactor could be useful for other purposes, even if it never propelled an airplane. So, after the program got scrapped, they continued in theoretical studies, and there was a grant from U.S. Atomic Energy Commissions for $1 million for new reactor concepts. And so overnight, they wrote a proposal, and I recommend this Molten Salt Adventure article by McPherson, where he kind of goes into how this thing got conceived. They reused the same cavity they had for the aircraft reactor experiment. And so they tried to save a lot of money they could, because they only had $1 million to work with originally. And they designed 8 megawatt reactor, which ran for 5 years in late 1960s. And the purpose was development and demonstration of many of the fundamental technological capabilities you would need to build these systems. So things like online refueling. Can you refuel the system online as it goes? So as it basically burns the fuel, can we just keep adding and have the system stable? Can we remove the uranium from the fuel salt just by bubbling fluorine through the salt? Can we vacuum distill the salt to remove the fission products of it? I think this is the only reactor core which run on all three fissile fuels: uranium-233, uranium-235, and plutonium-239. They developed a new high nickel alloy called Hastelloy N, and they found some corrosion issues and they solved them. And they designed many other sort of reactors which were to be the commercial demonstrators, but none were ever built. And you may know the story that in the early 1970s, Alvin Weinberg was questioning safety of light water reactors, which got him fired from the Oak Ridge Directorate, and that was kind of the end of the story here. Some pictures. So you see it was a reasonably tiny reactor. It was just 8 megawatts. Here you see a person on top of the reactor vessel. And what are its passive safety features? So one of the issues with these solid fuel reactors is that in case, when you are running the solid fuel core nominally, you want to make money. And you make money by taking the heat out of the reactor, running it through the heat exchangers into the power turbine and making electricity. So you want to minimize heat losses, right? Now, if you lose the ultimate heat sink, the turbine, condensers, or something happens, you need to bring cooling from the outside into that system. And that's when you end up with high pressure water injection, low pressure water injection as a safety systems, each of them backed up 3 times. Safety system in nuclear world means very, 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 very expensive because of all the regulatory overburden for nuclear safety systems. And then you may have to become very unlucky, have all the diesels in the basement, you get flooded, and there you go. So that's an issue. If you have liquid fuel, then you can use gravity to change the geometry of your fuel. You can't do that with solid fuel. Now, how would you do that? So here is the reactor core with pumps and the heat exchangers, and pumps pump the fuel around the primary pump. But here you have what's called a freeze plug. Freeze plug is just a section of a pipe which is connected to the primary system, which is flattened and actively cooled by a cooling system, a fan if you wish. If all the power disappears from the system, the fan or the cooling system stops cooling, the freeze plug melts, and then by gravity, the fuel drains into a drain tank, which is designed with a different geometry in mind and with sufficient cooling to cool off the decay heat to prevent any overheating. So that's a simple passive safety systems which you can implement if you have liquid fuel. And that's what they had in molten salt reactor experiment. This is the freeze plug, and these are the drain tanks. So why didn't it happen? And maybe that's too much of a long story, but try to make it quick. Quick story is that in Manhattan Project, we developed a lot of experience with uranium and plutonium. The Seaborg's work on plutonium chemistry was a breakthrough. We figured out how to use these 2 elements. Thorium actually was considered as when we figured out that the plutonium-239 from Hanford or from these type of reactors like the extended Oak Ridge will have unavoidable admixture of plutonium-240, then, which was in, I think, early 1945, people considered it to be a big problem. And one of the ideas to solve it was to use the plutonium in a light water moderated configuration to breathe uranium-233 from thorium. And they dropped it before even building it, recognizing that it's even a worse alternative than the plutonium. And the people here working at Oak Ridge, they didn't really know due to compartmentalization of the work that in Los Alamos they have figured out the implosion system, right? So this work was never really considered, and there was a lot of experience with uranium and plutonium, so people were more comfortable with it. If you have a fast reactor which doesn't moderate neutrons, plutonium can give you much higher breeding gains. Thorium can be a breeder even in thermal spectrum, which you cannot do on a uranium-plutonium cycle because of this resonance here. Again, I don't want to go into. You can ask me questions if you like, if you're interested in it. So, if you ask the people who are involved in this research, what were the reasons why this hasn't been done? The established industry wasn't familiar with this. It appeared as a daunting technology which is radically different from what the technology people were familiar with. It breaks the mindset of how we do reactors on sort of all scales. It's like the difference between typewriter and a computer, right? At the end, you have the same text on a page, but the mindset to use it, to get there, it's all completely different. And so it was deferred to future as something we may consider later. Another issue was that the other reactor systems where the light water reactor and liquid metal fast breeder system were developed all across the country in many national labs, and there was a great sort of familiarity with it across the nation, whereas the molten salt systems were only developed at Oak Ridge. And of course, this was before internet. So you get sort of organizational issues. And then the existing bureaucracy basically dismissed it as an Oak Ridge pet project. If you read Seaborg's diaries, here's a good book, a short book, Atomic Energy Commission under Nixon, Adjusting to Troubled Times. Glenn Seaborg was the chair of the U.S. Atomic Energy Commission in this decade. And he kind of gives you a different point of view than if you read what the Weinberg and other Oak Ridgers sort of wrote about the history of the project. They saw this liquid metal fast breeder as really the most promising of all the breeder alternatives. Nobody thought we could get away with light water reactors because they are so inefficient, and they thought we have much, much, much less uranium than ultimately we know we have. So they had these 5 assumptions which led them to push for the fast breeder development other than sort of purely political sort of reasons which were also present. That electric demand will double every decade, nuclear will capture more electricity market share, uranium will remain scarce, the development of this liquid metal fast breeder systems will be easy, and there will be available funding both from private sector and from public sector. And if anyone, at most 2 of these assumptions prove incorrect, that would be enough to bring the whole edifice tumbling down to the ground. In the actual event, none of the assumptions proved correct. So you may remember the Clinch River Breeder Reactor project, which sort of exploded in 1980s. The funding sort of became so expensive that the project got canceled in 1980s. So that's what he's talking about. However, people never went back to let's say late 1960s or 1970s, and reconsider the decisions which were made there. We sort of got stuck with the decisions made and kind of took the perceived wisdom of the past and ran with it. And currently, we have a very different circumstance than we had in the 1960s. So for instance, now people really worry about safety, and inherent walkaway safety is really desirable. Nobody worried about nuclear safety in the 1960s. Proliferation concerns, right? Nobody cared about proliferation. Everybody ran with high enriched uranium. It was not a big issue. Of course, this has changed in 1974. We thought that we need to create more and more and more fissionable actinides for the military complex. Now we have realized that we have way more than we need, and we are trying to find ways to get rid of the military plutonium and highly enriched uranium. We are worried about managing our inventory of spent fuels, for instance. Nobody really worried about that back in the day. So the boundary conditions have dramatically changed. I'm running out of time, so I'll try to go a little quicker. So what has happened? In the year 2000, the Generation 4 International Forum for sort of the next generation of nuclear reactors was formed and recognized that molten salt reactors as one of the 6 promising concepts in this next generation. In 2004, Oak Ridge started to work on salt-cooled system with solid fuel. In 2006, Kirk Sorensen made these papers freely available online and sort of tried to raise interest in them. In 2011, China announced as a national priority development of these molten salt reactors. And between 2011 and 2015, there were several new private startups in North America, and also some in Europe, to pursue development of this technology. And last year, China announced location of 2 prototypes for molten salt reactors to be built, and they went up from $500 million funding to $3.3 billion in funding for this program. This program is led by Jianmeng Heng, who is the president of Shanghai Tech University, president of the Shanghai Institute for Nuclear and Applied Research, and he was also a member of the Directorate of Chinese Academy of Sciences. And he is the son of Jiang Zemin, who is this guy, president of China, 1993 to 2003. So there's a reasonable support. So Shanghai Institute of Nuclear and Applied Physics leads this program. They had a collaboration with the United States and European Union to develop this technology. They basically started from starting fresh with about 700 fresh PhDs. And in those 5 years, they basically replicated everything the Oak Ridge has done in 50s, 60s, and early 70s in this project. So they developed domestic capability to create high purity nuclear graphite, which you need. They developed actually better ways to enrich lithium, which is a necessary component of this technology, or let's say useful, not absolutely necessary. They developed their own version of this high nickel alloy, and they tested a lot of salt loops, components like valves, pumps, flanges, and other things you need to build a reactor. And then they announced this program for 2 molten salt reactor demonstrators in Gansu province next to the town of Wuvei, which is on the border of Gobi Desert. And they expected the first reactor online in 2020s, and with wide range of applications, including large loitering drones. So what killed the aircraft nuclear program was that the need for shielding was just too much for aircraft to fly. But if you don't have people, they don't need the shielding. So I mean, I don't know. This may be just a paper of one, researcher somewhere. I don't know if this is real. Now the Japanese also have a program called Fuji. Japanese have a program, Fuji, for their molten salt reactor concept. Europe is pursuing a molten salt fast reactor. So this is the core with no internals. It's just a fast core where the fuel flows in these loops. That's the alternative to solid fuel liquid metal fast breeders to burn excess actinides, which are left up after you do the MOX fuel for light water reactors. But they aim for deployment after 2045. So I think if somebody tells me that something will happen after they retire, I don't take it too seriously. But their research program is actually very, very high quality and very good, but the funding levels are just not there. In the United States, we have a very different mindset about nuclear. And you can see this 2010 document from US DOE. It is the role of industry to design, construct, and operate commercial power plants. It is industry decision which technology will be deployed. It is the decision to deploy nuclear power systems is made by industry and private sectors in market-based economies. So we don't really have the government telling us what should we do as far as deploying the technologies. It's really up to industry. So let's talk about industry. Bill Gates funded a company called TerraPower. It was originally focused on a sodium-cooled fast system he called a traveling wave reactor. But they also have a sort of backup, much like the French, molten chloride fast reactor, which is a fast reactor. It uses chloride salts instead of fluoride salts. There are advantages and disadvantages of these choices. US DOE is actually funding a component test facility for the system, and they formed a partnership with the Southern company for commercial development of that technology. And this is their sketch. So here you see a bucket, which is empty, so no core internals. You just put the fuel salt in it, and then you pump the salt through the heat exchangers around. So seems like a very simple reactor design. Terrestrial Energy is a Canadian company, but they have a US sister company called Terrestrial USA. They are developing an integral molten salt reactor. This is the latest sketch I was able to find. I'm running out of time, so I'll just go quickly through this. This is how their power plant would look like. The one thing to note is that they have the primary system is here. It's generating heat. Clean salt goes through heat exchangers here. And then here it powers the steam cycle. The Terrestrial Energy currently talks about a steam cycle, something like you have in advanced coal plants, so pretty much off-the-shelf technologies. But notice that the steam cycle is far away from your nuclear island. Right? In a light water reactors, your pressurizers sit next to the reactor in the containment. If you wear them out, you have to cut the hole in the containment, take them out, bring the new ones in, close the containment. That's $1 billion at minimum. So you don't really want to thermally stress these systems to wear them out. Now, if it's in the building outside of your containment and it's just using a clean salt after 2 heat exchangers from the core, then you can ramp this thing up and down. And if you wear it out, well, you just buy another off-the-shelf steam turbine. Right? So if you think about integration with wind and solar, this seems much more beneficial. So they're currently pursuing loan guarantees. They are the first advanced reactor vendor which went through regulatory review. In Canada, they have a different system. There are sort of pre-licensing hearings which have 2 phases. They face the phase 1 of this vendor design review process. Currently, they are going through the phase 2 of this vendor design review. They assume that the licensing application with US NRC will start in 2019. I had a student who did, we did economic modeling in a top-down economic methodology called G4 Econs, developed by this Generation 4 International Forum. And we found that the cost of the reactor is roughly on par with what the AP1000 claimed to be, kind of the Chinese costs of AP1000, not the Vogel costs. And this is what the IMSR claims using bottom-up methodology, which we cannot really replicate because we don't have the design details, and it takes, it's much more work than you can do in one student. It's about $50 per megawatt hour, and this is compared to other alternatives. Now, this is Canadian gas, not US gas. There are other startups. Thorcon Power is a sort of an open source startup, so they publish all their technology openly. It was starting by Martingale Company, which is in shipbuilding. So they have shipyards. So the idea is sort of a shipyard building of these systems. They are looking at Indonesia markets, and they are trying to just scale up a molten salt reactor experiment with as little innovations as possible. So they can use the molten salt reactor experiment as a reference in their licensing. That's their approach. So this would be the reactor vessel with the pump, the heat exchanger. So the heat exchanger is horizontal instead of vertical as an MSRE. They have the drain tank, so it's closer integrated than in the case of MSRE. It's kind of optimized and rearranged, but it's really just the bigger MSRE. And then there's Flipe Energy, and the Flipe Energy aims to reach the holy grail of the thorium energy when our only input into the reactor is thorium. Thorium is non-fissile, so we have to do something with it. And we have the fissile element is uranium-233, which is being fissioned in the core, and as it produces neutrons, these neutrons transfer transform thorium-232 into uranium-233 fuel. And then using a chemical separator in the blanket, we take this newly formed U-233, put it back into the core, and then a chemical separator connected to the driver fuel salt extracts the waste, the fission products out. So here, the uranium-233 only sort of acts as a catalyst to take thorium and burn it via this reaction. And that was the original goal of the molten salt reactor program at Oak Ridge, where you don't need any enrichment. You can only feed it with thorium-232, and your waste are just the fission products. Much more challenging. And the reason why you would do that is that you can use a simple chemical trick to make this fuel cycle work. And the trick is that if you basically bubble fluorine gas through the blanket, then thorium only has valency 4, so it stays in tetrafluoride form, it stays in the salt, whereas uranium can jump from tetrafluoride to hexafluoride gas, and this way you can basically easily separate the uranium fuel from the blanket by this fluoride volatility process, bubbling UF6, and then you can the extracted UF6 can be reduced by hydrogen back in the salt and put back in the core. And you can accomplish it by standard off-the-shelf components. And there's also similarly easy, compared to uranium-plutonium cycle process, to separate the fission products. Now what we gain here is that instead of when we start with low-enriched fuel, right, we have some fuel, some uranium-235 and uranium-238. With 1 neutron absorption, we create plutonium. If we start with thorium-232, we have to go through this very, very long chain to create transuranic, which is neptunium-237. And you can irradiate neptunium-237, generate plutonium-238, which we need for space program, for the radio thermal generators. So I'm out of time. So just to summarize our big problem, this was last year energy consumption in the world, 2018 quads, 5.4 billion tons of coals and all the other sources. If we triple our energy consumption, we would need 20,000 tons of thorium to feed the world with energy, which is much less than current amounts. Of course, that's sort of road not taken, right? But now, thorium has this advantage that it's virtually limitless in availability. It's whenever you are mining for rare earth elements, thorium is, because it has similar chemistry as rare earth elements, it's found in the same mineralizations. So we are currently actually mining enough thorium to fuel the planet, but we just don't use it. So it's an interesting resource which is free, and it has all this potential, but the potential really isn't in the source, it's in the machine. So we have to develop the machines. So I'll conclude here. Clean, safe, affordable, and scalable energy is mandatory for humanity to thrive. I think that molten salt-based advanced nuclear power has many of the attributes we need to come up with energy cheaper than fossil fuels fundamentally. There's a broad range of concepts of these molten salt reactors. I talked about the simple burners, which are like molten salt reactor experiments. There is a fast reactors pursued by the European Union and Bill Gates. And then there is a two-fluid breeder by Flight Energy. So there's a whole sort of universe of possible designs. Europe and Russia lead this academic research in this area. China has a very well-funded Thorium MSR program based on past work here. And they have under construction first 2 prototypes. And in this country, we have several privately funded startups, which has some level of support from the Department of Energy. So thank you for your attention.
Because of our time limitations, maybe time for one question and then additional questions. You can just stay after for as long as Professor Chvala can stay. Any question, one question that we can ask within our time limits here?
I guess I'll go. You obviously obviously you mentioned the end goal is clean, safe, affordable, and scalable energy.
Right.
And I think you're absolutely right with thorium, and it's practically a proven technology, but I'm just curious what your opinions would be on some of the alternatives, because obviously wind and solar aren't gonna work, they only work a quarter of the time, and then like geothermal, hydro, and tidal are location-based. But then the two that are a little interesting to me are the potentials of fusion and low or no carbon dioxide emission natural gas plants. So I was wondering if you have opinions on those two technologies.
So the carbon capture is just expensive, right? So there's just adds the cost to what we are doing already. So I don't see that really being applicable to the developed world. We can do it here, locations which are. You also need a geology for the carbon capture, for the sequestration to work. So yeah, that's fusion. There might be a breakthrough. There are several private startups which are look at different ways of doing fusion. But if you look at the large-scale fusion experiments, if you look at ITER, $25 billion to euros or whatever, to produce 100 megawatt of heat if everything works out, with no tritium breeding, right? So I just don't see economically fusion. I'm not a fusion expert, but it doesn't seem to be. Our goal is not to make a fusion work. Our goal in fusion is to make it cheaper than natural gas, right? That's the way I'm looking at it. I think the good alternative to what I'm talking about is, for instance, NuScale. Right, so NuScale is a U.S. startup to do the light water reactors smaller and modular, and I think that has a lot of potential, especially in the near term. Of course, that doesn't touch the issues. I mean, it solves the issues with siting, quite a bit of them. It solves a lot of issues with the safety systems. It solves a lot of the economic issues with large reactors, but it has the same waste profile. So I think that's certainly in the next 2 decades, I think these small modular reactors based on known existing technologies, I think they have a great potential.
And I'm afraid other questions will have to be individual to Professor Chvala. And once again, we really thank you for this talk.
Thank you very much for having me.